Hi, welcome to our short demo on how we can use XGBoost and RAPIDS to be able to predict when hard disks would fail. So for this, we're using a dataset from a cloud storage provider called Backblaze, and we can see how it's actually very valuable for them to be able to predict when hard disks would fail in the future so that they can preemptively swap out these hard disks. So before we get started, let's just import all the libraries that we're going to use in the demo to get them out of the way first. And then we should also download our training and evaluation data. So as you can see, the files already exist on my machine, so there's no need to download them. Our first order of business is to load the training data. As you can see over here, we are loading the data from a CSV file into a pandas data frame. So one thing to note that in these two steps, we're actually loading the data into the system memory or system RAM instead of the GPU memory, although we can actually do that directly using cuDF. The reason why we load it into system memory is that we are also going to be training the same model on the CPU to compare the speed. So we are loading it to a pandas data frame first. And in this step over here, we're actually splitting the data frame into two different data frames, one which contains the training data and the other one which contains only the target labels that we want the model to predict. So basically, these target labels are whether or not the drives would fail 2 days from now. Next, we'll do the same thing for our evaluation data. You might notice that our training data actually consists of drive data from January 2015 to September 2018, and then our evaluation data actually comes like chronologically after that, from October 2018 to December 2018. So the idea here is that we want to use historical data to be able to predict future data. We have a couple of models for the decision tree model in XGBoost, so let's just get that out of the way here. So these are hyperparameters that a data scientist can possibly tune to make the model better. So our first order of business here is to show what it's like to be training using a CPU. So the CPU that we're using here is actually the Xeon CPU inside a DGX station, which is actually a very high-end Xeon CPU. So it has 20 hyper-threaded cores, which give us a total of 40 logical cores or threads that XGBoost is able to use concurrently for training. So let's see how long it takes for a CPU to do the training. As you can see over here, all 40 of our logical cores have been maxed out, and the training is not slow because this is after all a high-end CPU, but the timing leaves a lot to be desired. So for this relatively small model over here, it takes a total of 10.2 seconds to train over 120 iterations. Next, we'll see how it's like to be using the GPU for training. So the first thing that we're going to do is to use cuDF to move the training and evaluation data from our system memory into our GPU memory. So that's achieved using the code over here. And now we'll see what it's like to be using the GPU for training. And it's so fast that we don't really have a time to look at how it's doing during the training. But I can see this small spike over here that shows the GPU is being used. We can also check how much GPU memory is being used using the GPU stat package, and we can see that our small model over here is only using about 1 GB of GPU memory. Let's compare the time that we took between our CPU and GPU training, and we can see over here that we have achieved more than 4 times speed up by moving this relatively small model from a CPU to a GPU for training. We just have a small last bit over here where we evaluate the performance of the model that we have trained. So we can see here that our model has achieved almost 95% overall accuracy, but there's a bit of a class imbalance. So let's use the classification report to see how well it's actually doing. So the failure case is the one where we are more interested at, and you can see here that we have recalled about 61% of the cases. That means that for the hard drives that are going to fail 2 days in the future, we have successfully predicted more than 61% of those. We can also visualize this using a confusion matrix. So you can see that we have successfully caught around 61% of the failure cases. Naturally, we can do a lot better by increased feature engineering or increased hyperparameter tuning. but this serves the purpose of the demo.